All right, let's get this show on the road. Hello, everyone. Hope you're well. Hope that, wait, what? Wait for what? Oh, no, you can't watch it now. It's 18 minutes long. So you can't, you watch it after. Okay. Okay. So, exam is on Saturday, as far as I know. I could give it on Thursday if you guys want. We should be finishing everything by Wednesday. But it's on, the final is on the 23rd. So yes, the final is on Thursday. So I would give our test on Saturday, the 18th, and then the following Thursday is the final. All right, and when I find out more information on that, I will of course let you guys know. All right, let's get into another exciting episode of Math 212. Let me share the file with you and stop the video, and let's get this thing a-rolling. What we'll do from Monday through Wednesday. So yeah, I'm gonna miss you guys too, actually. Like, what am I gonna do in August? I'm just gonna be sitting aimlessly, just clutching my whiteboard, just like my tablet, no one to write to. Okay, yeah. So today we're gonna talk about multivariable functions, just some general basic definitions once again, just kind of introduce a concept. We'll start limits in higher dimensions. So we're going to look at multivariable limits. I think that's going to spill over into tomorrow, at which point tomorrow I will also finish limits and then start partial derivatives. And that will spill over into Wednesday. I should be able to finish that before the end of Wednesday's class. But by Wednesday, I see us finishing everything. So on Thursday, I don't know, we can maybe review for the test or maybe even start reviewing for the final. Hopefully I find out some more information on the final. What I'll do is I'll reach out to the course supervisor, ask if there's anything I need to know about this final that was different from the spring, and I'll relay that information to you guys. But yeah, let's actually jump into it. So this was a last week's lecture. Just to kind of remind you where we were. We learned how to sketch cylinders and quadric surfaces. Just a big thing about cylinders. Cylinders is when you take a curve and you propagate it along some axis. The curve is called the generating curve. We know that a non-planar cylinder, if it's not a plane, it's easily identifiable when you have a cylinder because you will have two variables in the equation and there will be a missing variable. Like there's a variable that visually is missing, which means you can sketch in the plane of the two variables that you can see, and then the missing variable tells you what axis you're stretching along. So you'll have two variables in the equation. The missing variable will tell you the axis that you are parallel to. Now, how you sketch a cylinder is, well, first you sketch the generating curve, as we call it, which is just like a 2D curve of the variables that you can see. And then you just kind of propagate that along an axis. We also looked at quadric surfaces. So this is like, take a quadratic equation and generalize it to the big three-dimensional monster that it could be. Then it turns out if you take certain values of the constants in that kind of equation, which is, it's just like this, like a generalized quadratic equation here. There are 6 possibilities for what that guy can visually show up as. It'll be one of these guys. Now, of course, we looked at the simple types. The most general type will still look like one of these. It'll just be tilted. You might not have them running along the X, Y, or Z axis. They might be running along like some different line. But this is the basic 6 shapes that you can get. So a quadratic in 2 dimensions is just a parabola. It's always going to be some sort of parabola. However, you bump up the dimension to 3, and there are 6 possible types of pictures that could arise. And this is already kind of foreshadowing, and we'll see more of this today, foreshadowing just how much a bump up in dimension can actually complicate matters a lot. And which is why we need things like learning how to deal with vectors and all that sort of things, because it does make sense. It makes dealing with higher dimensions a lot easier, even though we're not going to be able to always visualize it as well. The idea behind graphing quadric surfaces or anything that's not a cylinder is basically to draw traces, pretty much pretend one variable is a constant at a time, sketch what the resulting is in the other 2 variables, and then you put all these sketches together. You sketch from various perspectives and you kind of combine these together. And we did that procedure on many guys, and we did many examples of us sketching last time. So that's very important. And you saw in the quiz, basically what happens is I can either give you an equation and ask you to match it to a picture, or I can show you a picture and ask you to choose what equation would represent that picture. So on a multiple choice test, that's kind of what's going to be happening in regards to this topic. So hopefully those 2 problems, I think there were 2 problems. Hopefully those 2 problems on this sort of thing on the quiz went okay for you. Now let's go into functions of several variables. Okay, so the idea behind this is simple. We're used to seeing functions of a single variable. That's what we've been doing in our lives up until now. So we can have something like this, like your y equals x squared or something like that. So this was a function of the single variable x. X was called the independent variable, right? So when we're talking about functions of variables, we're talking about the independent ones. So the several variables here represent the independent variables. So here we have several independent variables. Before, we only had one, something like an x, for example. So y was the dependent variable, x was the independent variable. X was the variable that got manipulated, and then you saw the results of that manipulation in y. Y tells you the result of the manipulation. It connects what the x is doing to some function or some value that you care about. Now, the thing is, as you might, well, for sure you guys know by now, is that life is sometimes more complicated than can be expressed by a single independent variable. There are times when you need more than one variable to talk about a single thing. For example, if you wanted to judge how healthy you are, let's say you're concerned about your health, you go to the doctor. It's not just one number that's going to matter, right? When your doctor gives you the function of how healthy you are, it's not just one number that he looks at. He looks at several numbers. What's your age? What's your height? What's your weight? What's your blood pressure? how's your blood sugar? How are your hormone levels? There are tons of measurements that can be taken, and all of these measurements would go into being able to conclude this person is healthy, or this person needs to watch their diet here, or this person needs more exercise, this person needs more vitamin D, like this person is not healthy, or they're well within the healthy range. To be able to make a single conclusion about one individual, several independent factors, or maybe not so independent, have to come together and to give you the full picture. Or maybe you're examining some company to try to see how viable a stock is. If you want to buy stock in that company, there are many numbers that you would look at to talk about this one company. Like, how many employees do they have? What is their debt to income ratio? How many years have they been in business? And all this sort of things. There are many numbers. There are times in real life where you need several independent variables to make an informed decision about some other dependent variable. So in this case, in the last example I just give, you just want an output that says buy the stock or don't buy the stock. It's just a 2-value output. However, to be able to say that, give that reasoning for the 2-value output, you need many independent values that you consider together. So functions of several variables generalizes functions to this kind of situation where we have several variables. Okay, and so here we can have a function that depends on a single variable that's written as a function. Sometimes we can't write it as a function specifically, like a circle, but we still have the idea that the y is kind of the dependent one versus the x is the independent one, etc. We want to take that and we want to actually generalize this idea. So what we're going to do is we're going to start by looking at functions of 2 variables. We're going to look at what that would how to kind of maneuver ourselves in this regard. We'll also look at 3 variables, but then everything else I'll just kind of mention generalizes more or less naturally to what we've been doing. So right now we're going to look at functions of 2 variables specifically. So here we have a function that takes 2 different inputs, and we are concerned with having 1 output, right? So these are real valued functions of 2 different variables. So the input space is 2-dimensional. There are 2 values that we can take on, say x and y. And the output is going to be f of x, y, which we often call z, right? D is called the domain of f. This is where all your coordinates live that you're plugging into your function. And the range is just the outputs on the z-axis. So how does this work? Well, basically you have this region D that we call the domain of the function. You can have coordinates there, and I can take a random coordinate here, like whatever, maybe -1, 1. And then I plug it into my function, and the function is going to output a certain value. It's going to give me a value at -1, 1. And so my input space is 2-dimensional. My output space, however, is still 1-dimensional. There are going to be classes for some of you in the future where even your output space can be multi-dimensional, but for now, let's look at it this way. Okay, so that's the kind of idea we want. We have 2 inputs giving us 1 output, right? Now, let's talk about the domain here. Now, another name for a domain that is often used in this higher dimensional context is the term region. And when it comes to region, there are some definitions that you want to know. I didn't put these in a box because these are things you should know. I believe, however, they're more important for higher level classes. I don't really anticipate you seeing questions that have to do with these things. I might ask you a question or 2 on them just to be safe and cover our bases, but they are important definitions, and a big chunk of the chapter, this section in your textbook, goes into really talking about these. So I don't want the course supervisor to say, let's test them on this, and you guys don't know. So I'm going to explain to you what a region is. Pretty much just think of this as the domain space. However, there are several different things that you want to know about them. One is, what is the interior of a region versus the boundary of a region? The interior, we all have very intuitive concepts for what this means. This is just stuff on the inside. But technically, mathematically, what interior means, something is an interior point if I can open some disk around that point, it doesn't matter how small, that will remain within the entire set. It will only contain in that disk points in the set itself. This point, we say, would be an interior point. Something is on the boundary or the edge. It basically means if I am at that point, then no matter how small I create a disk with that point as the center, that disk will necessarily contain points outside of the set as well as within the set. So any such point is called a boundary point. When a set is open, it means that all points are interior points. And if a set is closed, means that it contains all its boundary points, meaning it contains all the interior points as well as the boundary points. We call that a closed set. Something that only has a boundary is also called a closed set. So just so you know. We often also distinguish between unbounded regions and bounded regions. Unbounded just means it goes on forever. That's the intuitive definition. The mathematical definition would be it's unbounded if I can open a circle, no matter what size circle I open at the origin, there will be points in the region that are outside that circle. So here, notice I open a circle at the origin, there are points outside. And I can open a bigger circle, and there'll still be points outside. Unbounded region means there will always be points outside of any circle centered at the origin of any finite radius. That's what unbounded means. Bounded basically means it's possible to get a circle centered at the origin large enough so that the entire region is within that circle. Each point in the region is closer to the origin than the circumference of that circle is closer to the origin. It's closer to the origin than the radius of that circle. So once you can enclose a region in a circle centered at the origin, we say it's bounded. If you cannot do this, we say it's unbounded. Now, let's get to the nitty-gritty, the part that everyone likes. when it comes to actually working with functions and evaluating them, finding domains and ranges of and all that stuff, it's all actually very intuitive. It generalizes very nicely from what you already know. So it is still the case that you can only take the logarithm of positive things. It is still the case that if you have an even radical, what's under that radical must be greater than or equal to 0. It's still the case that you can't divide by 0. So if you have a fraction, you have to make sure the denominator is not 0, et cetera, et cetera. All these little tricks and things that you knew about domains from single variable calculus and from algebra, those things still hold true today. There are some differences, however, because you're keeping your eyes on two things at a time when it comes to the domain. The domain is no longer an interval. The domain is now a set that has to be described in terms of coordinates or some sort of two-dimensional representation, where an interval is just something that runs along an axis. It's a one-dimensional thing. So there are little nuances like that that we'll get into as we do some of these examples. But other than that, it's very intuitive, which I don't really feel the need to even get too technical right now and describe everything. I think we can just learn by doing. No wax on, wax off needed here. We're just gonna jump in and start doing some stuff. So, okay, let's go with this. You guys kind of tell me where your intuition is leading and we'll deal with it. First question, find the domain of this function. Let's speak this a little bit bigger. So suppose I ask you, here's a function, z equals ln of blah, 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 right? So my z is like my function. It's like my f of x comma y. X and y are the inputs. What would you say is the domain of this function? This is for you guys. Domain of this function. All real numbers x. You've only told me about one of the inputs. All real numbers x and y. Tell me about what do you know about the logarithm? What is the domain of a logarithm? So if I were to ask you, what is the domain of ln of something? What would have to be true about that something? It's not greater than or equal to 1? No. It has to be positive, right? Meaning the x must be positive, which means it cannot include 0. So here, what do we need? So I know when I'm plugging something into a logarithm, it must be positive. So give me an expression, an equation or an inequality, something that would describe to me when this logarithm is going to work. Right, you need x squared plus y squared to be strictly greater than 0. Does that mean that any x and y values can work? Are there any restrictions on that requirement? Are there any values that I cannot pick? No, no is answering which one of my questions. Are there values that I'm not allowed to pick here? Yeah, you guys are still thinking in a single variable mindset, right? Because when you tell me 0, 0 for who? There are two people here. Right, but that's still not good enough, because if I can say my x is 0 and my y is 1 and it'll work. Right? That works. So when you say 0 for both, describe specifically what do you mean? It's very important that you can get very specific with this thing. All right, so this means you need x not equals 0 and or y not equals 0. Meaning both cannot be 0 at the same time. Meaning pretty much any point in the 2D plane is okay except the origin. Meaning the domain of our function is the set. It's all possible coordinates of xy such that xy is not the origin, right? Or you can say this is the same as all possible coordinates such that x not equals 0 and at the same time y not equals 0. And it's very important that you put and here and not or, because the or can work. So that would be the domain. Here's how I would describe it. You have to tell me what both the x and y's are doing. So you can't just say, oh, it's 0 or all real numbers. What does that mean? Which one of the variables are you talking about? And can I choose it for both of them, each of them? How do each have to behave together? So now if I were to sketch the region, sketch where this thing actually works, then the domain is a bad point, does not work here. However, everywhere else is fine. So the entire plane except the origin is going to be the answer here. That's the domain. Now, hopefully you guys are getting that, but we'll have other examples. Okay, so let's try this example right here. See if you guys are getting how you want to look at this now. Okay, so here's an example. Don't know why these guys decided to combine themselves just now. All right, so do the same thing for this problem here. And hopefully you can see that. Let me make this a little bigger. Okay, so hopefully you're seeing that. Okay, answer the same question. Domain of that function. Come on, guys, where are you? Did that quiz like make you guys tired? Come on. Y and x not equal to? Why is, well, why can't x be 2? What would be the problem if x were 2?
Well, the thing is, if you have y equals 2, then on the bottom you would have a 0. So then, and the thing is, you can't divide an equation by 0.
Right, so y equals 2, definitely bad. Now, the x?
So on the top, if you have y equals 2, then that would be x plus 4 minus 2, which would be 2. So then you would have x plus 2. So then if you have that, that would be 0, which you can also do.
Right, the square root of 0 is fine.
Yeah.
Give me, so for sure, I know.
But you can't do the square root of a negative number, right?
Right, so that's what
So
you're
then
thinking.
with
So
that,
first there's the denominator.
yeah.
So for the denominator, we know that y cannot be equal to 2. Now, what's the numerator? What is the requirement on the numerator? If you had to say, what is the requirement?
X has to be greater than or equal to 2, which means x can't be less than 2.
No, because now you're leaving out the y. Did you notice there's a y
Oh,
squared there?
yeah. So then that means y also can't be 2, and then
No, you can't isolate them.
you can't.
So what's in the chat is correct. Everything that's under the radical needs to be
Oh.
greater than or equal to 0. So x plus y squared minus 2 needs to be greater than or equal to 0, which means x plus y squared needs to be greater than or equal to 2. So you shouldn't be breaking them down individually and say, oh, your x has to be greater than 2 or your y has to be greater than 2. No, they both, the combination x plus y squared, that whole thing needs to be greater than or equal to 2. So we have two requirements here. Now, this would, of course, mean your x must be greater than or equal to 2 minus y squared. And this is going to come in handy when we want to visualize that, because now we can see that, oh, that's kind of like a quadratic. So I would say here, the domain of f is the set x comma y such that y cannot be 2, comma, as well as your x must be greater than or equal to 2 minus y squared. Now, what that would look like, so that would be the domain. Now, what that would look like, hold on, give me a second. Okay, I'm back. Now, what that would look like is, well, if I were to actually try to sketch the region, my vertical lines are all over the place today. It's because I'm not making the sound effects. If I were to sketch the region, what does this region actually look like? Well, x equals 2. So when your y is 0, that's of course at 2. X equals 2 minus y squared is going to be, well, that. Because when y gets bigger, the x gets smaller. And we know that it hits here at when y is a radical 2. Which means there's a point above here where y is 2. Okay, so y equals 2 is bad. I cannot touch anywhere on this horizontal line. On top of that, I need my x to be larger than this parabola. So it's all regions outside this parabola, not including the red dotted line. And in fact, it includes the boundary except the part that is on the red dotted line. Right? So the region in space where this guy would work is that. I'm allowed to plug in inputs from anywhere in this green space. I'm not allowed to plug in inputs down here. So for example, I cannot plug in the origin. If I were to plug in both x and y equals 0, I would get a negative under the radical, etc. Right? So Again, you guys are still thinking of isolating X and Y and talking about X and Y separately. No, you have to keep two things in mind at the same time. You have to just make sure the entire expression behaves how you want it to behave. What the entire thing under a radical needs to be greater than or equal to 0. The entire thing under, if the entirety of a denominator cannot be 0, if something inside a logarithm, you can't have it being 0 or negative, etc. No, nothing on the red line can work. Because everything on the red line is where my y is equal to 2. So that would cause a division by 0. So nothing on the red line works. The red line is excluded. So it's all this green space, but you're not allowed to pick a point even in the green space where you're on the line y equals 2. Okay. Don't say you miss single variable domains. I mean, it just takes some getting used to, but once you get used to it, it's actually a lot more interesting. Single variable calculus gets boring after a while. Trust me, I know. You'll be fine. It just takes some practice into making sure you're keeping your eye on two things at a time. It's not just what is the x doing and what is the y doing. It's what is the expression that contains both x and y? How is that expression behaving? All right. What about evaluating a function? What is f of 2 comma 3? Now remember our f is this guy right here. So if that's our f and I ask you, what is f of 2 comma 3? What would you tell me? What would we do, first of all? What do you think we do here? Yeah, you plug what in? Right. So you would say plug in x equals 2 and y equals 3. Now I mean, I ranted about this. I don't think I ranted. Did I rant about it with my Calc 2 class? Anyway, there was one semester where I was teaching a class, and I believe it was pre-calc. Oh, undo. I believe it was pre-calc. And what I decided to do that semester is, normally I give a quiz every week when I'm giving in-person classes. But that for the pre-calc class, I decided that I would give a quiz every other week. And then on weeks where I don't give a quiz, I would give like this mini little seminar where I kind of rant and give advice. And one of the weeks, the theme was language and how important language is in terms of your cognitive abilities, in terms of learning math, in terms of learning science, in terms of learning anything technical, anything non-technical really. Language and how you phrase things is very important. So I don't want to harp at this, but when I'm kind of picking at you guys to say, oh, what are you plugging in? Who are you talking about? It's very important that you realize that the moment you connect a language that's not efficient to some process, you're going to end up getting in trouble. So when you say something like, I ask you, what is f of 2 comma 3? And you would say something like, plug it in. Plug it in, if you were to take what that means in English, it kind of says you're talking about one thing, right? So to say plug it in, not good. You don't want to do that. And I know it seems like I'm being overly technical here or overly pedantic, but really, your thinking process is very intimately connected with your language processing. So if your language is off, it's going to be very easy for you to mix up important concepts, mix up nuances. A lot of times you guys joke all the time about, oh, math causes you trust issues. The reason why you get confused with math, where you're in a situation where you can be convinced that you got the right thing, but you don't have the right thing, that misidentification, that missing of the nuance, I'm telling you, 98% of the time, it's a language issue. You thought of something in a certain way in your head, and you use words that don't really align with what the mathematical concept is, and so you end up coming up with some erroneous assumption that doesn't really fit, right? And then it's like when someone shows you the answer, it's like, man, this is why I have trust issues about it. But it's not trust issues. You never actually, it's like when a guy has a girlfriend and she complains about something, like, girls are crazy. And then it's like, no, she reacted this way because she said this thing and you didn't listen. You know what I mean? So it's very kind of weird when you're going to end up in situations where you're going to end up confused, you're going to do the wrong thing, and you're going to be sure that you're in the right, and then suddenly you find out you were wrong. And yeah, some of the times it's going to be because you didn't study and whatever, but a lot of the times, if you are one of the people who you study all the time, you do a lot of work, then one of the reasons why you can mess things up is language, believe it or not. How you can say things in language is very important. So if I ask you about a multivariable function and you say something like plug it in, you have to be aware that your language is suggesting that you're thinking of a single thing, when in reality, you should be thinking of two things. Your language needs to reflect the fact that you're thinking of two things. It's more important than you realize, trust me. Okay, so don't say plug it in. Say plug in this for X and that for Y. So you're clear that you're training your brain that in this scenario, you think about two things. You don't think about one thing, right? Very important. So here, you see f of 2 comma 3. Yes, you plug in x equals this, y equals this, right? When you're up here, you don't think, oh, I just need my x to be greater than 2. No, there's no just x. It's x and y. You're thinking of what do they have to do together, right? So same thing here, plug in x equals 2 and y equals 3. So here we would get the square root of 2, I'm going to plug in 2 for x, plus 3 squared all over 3 minus 2. Now the denominator is going to be 1, and what we're going to have here is the 2, subtract each other, you'll just get 3. Okay, language, it's important. In fact, in mathematics, language is more important than it is in a language class. I kid you not. Like a lot of people think, oh, I have to pay attention to grammar and language and subject-verb agreement and all that stuff in my English class. No, you need to pay attention to that in your math class more than anything. Like seriously, if you miss that, then I apologize for the education system. But seriously, if you're learning something technical, language is more important. Even more important than in your language class, because language in and of itself is not a technical thing. Like language rules and grammar, they're arbitrary. They're based on culture and all these things that don't really have to do with anything structural, right? But once you start to use that language to describe something structural, the structure of the language now starts to matter. It starts to matter more than normal. Like when you're in a creative writing class, you can say the same thing in a million different ways, use similes and metaphors and all sorts of things, and you can say something without actually saying it. In a technical subject, you cannot do this. You have to say exactly what the thing is that you're talking about. And you have to be very important, because if someone misses one of those technical cues, they end up getting a problem wrong, right? So in math class, language is actually even more important. A lot of students, when they're studying, they go on and they just jump into doing examples. Really? Did you actually read the definitions? Did you take notice of when the word or is used versus when the word and is used? Did you notice when if and only if is used? Did you notice when there was a one arrow versus a double arrow? Do you notice when there's something equal or greater than or equal to or strictly greater than? You have to notice these things, right? The language is very important. I wonder if I can just, oh. I erased the thing. So yeah. Language, very important in mathematics. It's more important than in your language classes. Okay, so plug in x equals 1 and y equals 2. All right, and what would we get here? Yes, that's better for you. What would I get if I plug in x equals 1 and y equals 2? Right, undefined. Because you end up with a division by 0. Which we know is illegal. Okay. So again, the intuition is the same behind single, like when you're looking at functions in a single variable. The difference is 2 things at a time. Think of 2 things. And this has to be reflected in everything, in your language, your mannerisms, how you think. You have to always be aware. I should be thinking of 2 things every time. There is no it, there is they, right? Okay, let's talk about this guy right here. Find the domain and range of this guy. Okay, go. What is the domain and range? So the domain for x and y is all real numbers. So x and y can be all real numbers. Okay, so here's how you would write that down. Okay, so it's very important. So we're used to thinking of all real numbers as like minus infinity to infinity. But I want you to appreciate that that only works on an interval. It does not work here, right? Because there's no interval. It's not a one-dimensional space. Our input is 2 dimensions. So every time you're describing domain, you have to describe what 2 things are doing. So you can say something like x comma y is an element of R2. That's one way you can say it. Another way you can say it is set of all x, y such that x and y are real numbers and there's no restriction. So something like that is how you can say it. What about the range? Tell me about the outputs. Someone tell me what the range would be. Oh, you can't see the function. There it is. The range of this function. Greater than or equal to 1. What is greater than or equal to 1? What does the range describe? Right, F. The range describes the output, right? The Z values in our case. Okay, so you want to say, don't just say greater than or equal to 1, say Z is greater than or equal to 1. How do you write that down? In this case, interval notation is okay. And it's okay because we're describing one thing. There's only one dependent variable. Right, so pretty much we have like, you can think of the Z number line. And we're allowed to pick anything that's 1 or bigger on that number line. So you're allowed to use interval notation here because interval notation is used to describe one-dimensional things. An interval cannot describe a two-dimensional thing or anything higher dimensional. Now, what you could also say is something like, if you want to use a set notation, you just say the set of all z such that z is greater than or equal to 1. Now, how do I know that z has to be greater than or equal to 1? Because your z is equal to 1 plus x squared plus y squared. Now, what do you notice about x squared is greater than or equal to 0 and y squared is greater than or equal to 0? This means that x squared plus y squared would be greater than or equal to 0, which means that if I add 1 to this, 1 plus x squared plus y squared, adding 1 to both sides would be greater than or equal to 1. And this thing here is your z. So you're basically saying your z can be greater than or equal to 1. So you figure that out, and then you go back up there and you plug that in. So you can use the set notation if you want, but just be aware you're allowed to use interval notation for the range because your range here is actually describing what one guy is doing. Okay, let's go. Did I get it, everyone? Okay. Ooh, graphing. Let's talk about graphing in higher dimensions. Now, just as before, the graph of a function is just a set of all points, x comma y comma z in R3. What are all the coordinates that fit in the equation of this thing? What are the x and y values and z values that all go together in some equation? So basically the idea is when you come up with your inputs, they're down here. So you have some sort of input point down here in x and y, but then you plug it into your function and it outputs some z value. So it has this output out over here. And basically for every point here, you can do that. It will plug in some point based, and the height of that point, the height of this is f of xy. And you just measure a bunch of different heights and you end up with drawing out this, this surface. So that's how you can understand the graph of a surface. Again, you plug in things in some region, in some domain. The output raises you above or below the xy plane, or maybe on the xy plane if your output happens to be 0, and you end up graphing something. So let's look at some examples of that. If I were to ask you to sketch the graph of this guy, what would that be? F of xy equals the square root of x squared plus y squared. What would the graph of that be? Is anyone there? Bueller? Ellipse? What makes you think of an ellipse? What does an ellipse look like? Maybe I should ask you that. Let me put it this way. Remember, you can think of your f as z. So what this is basically saying is z equals the square root of x squared plus y squared. What is that? So now this goes back to what we're doing on Thursday, tying it all in. Not an elliptic paraboloid. This is what we call a cone. A very important equation. I told you specifically that specific equation is very important. At least the top part. The graph of this looks like that, right? And it goes up forever, of course. So that's actually a cone. And one way you can think about this is that, well, the traces, they look like x squared plus y squared equals z squared, which is circles of radius z. So pretty much when your z equals 0, you have a circle of radius 0. When your z equals 1, you have a circle of radius 1. When your z equals 2, you have a circle of radius 2. You just have all these circles lining up. And they get bigger as you expand, go upwards. So that's actually a cone. So the graph of that was a cone. What about this one? Anyone? Again, to make this a little bit more intuitive, you just write a Z in that place. So what is that? What's that equation? It's a plane. I'm not sure if I like the question mark. Like, is that a plane? Like, we should know what a plane looks like, right? This is a plane. In fact, I can write it as 2x plus 6y plus z equals 6. Now, how do we sketch that? How do we sketch the plane? What was the procedure? Find x, y, and z intercepts. How do we find the intercepts? Let's say I want to find the x-intercept. How would I do that? Right. You make y and z equals 0. So you set two variables equal to 0 at a time. You solve for the third, you get the intercept. So for example, if I plug in y and z equals 0, I would get x equals 3. If I plug in x and z equals 0, I would get y equals 1. And if I plug in x and y equals 0, I would get z equals 6. And so that So that creates the plane. So that's the equation of a plane. So this comes, it's bringing it full circle. All these things that I told you about last time, cones, paraboloids, planes, it's coming back. You need to know what they look like as pictures. So those shapes that I gave you last time, they actually show up as graphs of two variable functions, which is another reason why you want to know how to sketch the other things. Because now when you see a function of two variables, you can imagine them as something like a plane or a cylinder or one of the other things that I mentioned. Okay, let's see here. Here's another important concept, the concept of a level curve. Now, you guys have definitely seen level curves in your life before. Have you ever looked on a map? If you've never looked on a map, which is possible in this day and age, have you ever looked at a GPS? Right? Like it's the same thing, right? Level curves are pretty much what a function or a graph is doing at different levels. How are these levels defined? Well, the level curves are all the curves that are of the form when you plug in the dependent variable equals a constant and you sketch that out. So there comes a point where you're plugging in, say, z equals some constant, right? So you have like z, this flat plane here. So this is like z equals 30 or whatever. And that will trace out a curve that when you map it down, it traces out this curve right here, which I think is the 30. Right? So that thing that in this example looks circular would be called a level curve. So you can actually look at this thing in terms of level curves. So you can think of a bunch of curves like and they kind of trace something out for you. Right? So of course you see what a level curve hopefully is doing. It takes something that would exist in 3 dimensions and it gives you a 2D representation. So what you'll notice is for the level curves, are 2D level curves of a 2 variable function. Our 2D representation, it is, you can think of it as projection, but it's not quite a scalar projection. Because scalar projection, we deal with that with variables and you're kind of doing one projection. But here you're projecting multiple things. You're thinking of you're projecting multiple things. You're projecting multiple curves that you get by slicing through some object with a plane, and it creates a bunch of cross-sectional curves that you then project down. You project those curves down. So maybe a 2D projection would be a nicer word to use. 2D projection of an object that lives in 3D. Now, level curves are really nice because it allows you to have some concept of what's going on in 3 dimensions by looking at something in 2 dimensions. So yes, in real life, in the 3-dimensional world, there's this mountain. However, we can represent that mountain on a piece of paper by just doing level curves, which is, in our case, a contour map or a topographical map. So these curves in a 2D space really are representative of something that's bigger than that space, that lives in a higher dimension. It's kind of like you're using the shadow of something to judge properties about that thing. Now, you'll never fully be able to appreciate what that thing looks like in 3 dimensions, but you can get a lot of information about the thing from its shadow. And we're going to get something really cool out of that later. So for example, the level curves of this guy, this is a guy that we sketched earlier, the same guy. Right? So what would be the level curves of this guy? So what are the level curves of this guy? Do-do-do. Do-do-do. I didn't want to get rid of that. Didn't want to get rid of that either. So this means you just cut up a bunch of levels. So something like z equals 0, and you would boop, get that level curve. Then you go to z equals 1, or you know, f of xy equals 1 or whatever, and you would get a slice coming through here that looks like a circle that you can project down. You want to do that in a different color. Let's do all of these guys in different colors. So let's say yellow, 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 yellow. Okay, so z equals 0 is this level. Then you go up a notch and you have z equals 1. That creates another curve here. And you can project that down into this circle here. Then you can plug in, say, z equals 2. And that would slice through your object at the level of z equals 2. And then you can go to z equals 3. And you can slice through that object here at z equals 3. Anyway, these guys would project down. And so what you can do is you end up with the idea of the level curves. So basically, you would have, in this case, the level curves just look like a bunch of concentric circles. So there's the guy that's at the origin. Then there's the guy that was this. Then there's the guy that is that. Then there's the guy that is this. Right? So that's what the level curves would look like. It's just a bunch of concentric circles for this guy. Similarly, we can plot the level curves of this guy. Okay, rapid fire. What's this guy? Z equals x squared plus y squared. What is it? Remember the name? Well, I wouldn't really call it elliptic paraboloid because it has the same values for the x and y. Technically, it would be sort of a circular paraboloid. Although you don't have to identify that circular paraboloid. The idea is this guy would look like not quite a cone, but it rises up slower than a cone. It gets steeper and steeper the higher you go up. Of course, it also goes on forever. But you can do the same thing. You can talk about level curves, and then you can slice it here, and you get this curve that projects down. And you can go one more level up, get this curve that projects down. And you can go another level up, projects this curve, projects down. Now what you get when you do these guys, now you'll get something that looks similar, except I wanted you to do these two examples just so you can do a comparison. Here's what you'll notice is happening here. Notice that because it starts out slow and gets steeper and steeper, you get to a much higher level in a shorter span of space. So the higher up you go, you'll realize that the closer the circles are. So you start there, and then you start farther away with the blue, but then your green gets a little closer. Then your red gets a little closer. Then you might have other things getting even closer than that. Because it starts to get steeper and steeper as you go on. And you'll notice here, the circles get closer to indicate we're getting steeper as we rise. And of course, if I especially start labeling all these curves, you can see that. So here's how the level curves can do us. So I might have done a level curve for one thing and I got this picture, and I look at a level curve for another thing and I got this picture, and these two pictures are very similar together, right? So if you look at these pictures together, they're very similar. Let me actually make this one. You'll notice that these guys are actually very similar as far as the pictures go, but they have enough difference between them where I can actually distinguish. So I can live in a 2D world where I can notice the difference. I can look at this and notice the difference between this and this, and I'll be able to say, I don't know what this thing looks like in 3 dimensions, but this one gets steeper and rises faster and has a steeper rate of change as we move out than this one. So I can tell you that this rises at a pretty much steady pace, whereas this one rises and gets steeper and steeper over time. So I can look at these two pictures of a bunch of concentric circles, and I can actually tell the difference between the two, right? So in that way, I can actually say what's going on in 3D by looking at a 2D representation, which is very useful because once you start getting to 3 or more variables, things start getting a little bit sketchy, let's say the least. Sketchies, or probably better to say unsketchy, in the sense that now we can't even sketch them. We can't even visualize something. So obviously, if a two-dimensional, if something of 2 variables, the graph of that is something that we draw in 3 dimensions, what do you think a function of 3 variables, what dimensions would that graph be in? That's right. This guy, if I were to sketch graphs of these guys, they will actually be in the 4th dimension, in 4 dimensions, which already now we can't visualize them. So one way in which we can study guys like these is to look at their level curves, because the level curves of a 4th dimensional thing will actually be surfaces in 3 dimensions. So here you are as a 3-dimensional object, you actually would cast a 2-dimensional shadow. So someone can look at your shadow and judge a few things about you, but of course they'll never be able to fully see what you are as a 3-dimensional being. So beings that live in 2 dimensions can't comprehend what you would look like. However, they can look at your shadow and they can start to talk about something like that. But then if your shadow could project something, if we look at something that lives in the floor, in the plane on the floor, that thing would only be 1-dimensional. Now that thing can't imagine what a 2-dimensional thing would look like. Everything to that thing would look like points and lines. Can't possibly comprehend what a 2-dimensional thing would look like. In the same way, now when we're going into 3 dimensions, it's very hard to comprehend. We can only, if we visually want to see or sort of imagine what these guys are doing, we would have to look at level curves, and these are their shadows, quote unquote. But the shadow of something in 4th dimension is actually becomes a 3-dimensional object, which is crazy when you think about it. Right? So everything that you can see in 3D, it could be just the shadow of some other object that you can't even comprehend in another dimension that's being projected in your reality in some 3-dimensional figure. Now, that's, I'm going to stop there because it can get really heady and very crazy at this point. So let's actually just talk about the math, what a Calc 2 student would know. Again, everything very similar in terms of how the math is going to work out. So if I were to ask you about the domain, it will be a very similar thing. But now you're looking at 3 things at a time. So the domain is, I'm looking at X, Y, and Z for a 4-dimensional thing. So I can have W equals a function of F, Y, and Z, which is often what we call it. We often call it W as the next guy, right? And I can say something like, well, I need that Y minus X should be greater than 0, and at the same time, Z cannot be 0. Right, so we can talk about that. Again, very intuitive, nothing much to say about that. But we can also talk about level curves, which I was just rambling on about just now. So a level curve and is this the last thing we're going to do in this section? I think it is. Right. So I just want to finish level curves here, talk about these two. So we didn't get to limits today, but it's going to be fine because I think we're a day ahead. So find the sketch of the level curves of this. So if we have W equals X squared plus Y squared minus Z squared, this graph is in 4D, Ultra HD. I'm kidding. Yeah. Well, you can't scroll up to the last problem. This. Yeah, so a lot of the math is going to be very similar in terms of what domains are and all that other stuff we're doing. But when it comes to visualization, it gets infinitely more complicated because you can't imagine what a function of 3 variables would look like. His graph would exist in 4 dimensions, which, trust me, you cannot imagine what that is. However, we can examine it based on level curves. So for example, here, level curves become level surfaces. So here we had a bunch of curves that would describe what this object in 3 dimensions is doing. Now, if I set W equals a constant, you would end up getting X squared plus Y squared minus Z squared equals a constant. And then you can plug in constants. So for example, if you plug in, say, K equals 0, that would give you Z squared equals X squared plus Y squared, which you know is a cone. Great. But what if you plugged in K equals 1? Well, that would give you that Z squared plus 1 is equal to X squared plus Y squared, which is a cone that's shifted down 1 unit. And if I have, say, K equals minus 1, this would give me Z squared minus 1 equals X squared plus Y squared, which is a cone shifted up 1 unit. So now when you start to draw the level surfaces, here is what it would look like. It's like you'll have cones inside of cones, inside of cones, inside of cones, inside of cones. Going up forever. And also, you will have like cones going down forever. You have cones inside of cones, inside of cones. And then you have cones outside here coming down, right? You get this really, it's like a leaflet thing. It's like a Russian doll. Like you just have cones inside of cones inside of cones. And what is this thing that is cones inside of cones inside of cones? Well, it is the shadow of something in 4 dimensions. and it represents itself as in like this Russian doll kind of object in 3 dimensions. What does this thing look like in 4D? I have no clue, and no one does. But I know its shadow looks like this, and sometimes you can glean information from the shadow. So like how we had concentric circles here, which was the level curves of this thing in 3 dimensions, we have concentric cones, which is the shadow of something in 4 dimensions, which is, yeah, big kind of a mind warp or whatever, but yeah. Similarly here, these guys, if I have W equals X squared plus Z squared minus Y, and set W equals K, this means I get Y plus K equals X squared minus Z squared. And of course, that is a paraboloid, right? And it has different levels. So for example, if I get K equals 0, this just gives me Y equals X squared plus Z squared. And that is just like a paraboloid running along here, center of the origin. Plug in K equals 1. Then that is a paraboloid starting from -1, going up. I plug in K equals -1. That is the paraboloid starting from 1, going up. And etc. And so I can look at the level curves of this guy, this creature, whatever it looks like in 4D, no one has a clue, but the level surfaces would look like a bunch of concentric paraboloids. It's this, a paraboloid inside a paraboloid inside a paraboloid. Kind of the same way in which our world is on the back of a turtle. And what's that turtle on? On the back of another turtle. And it goes on forever. And that is the shadow of some 4-dimensional object. It represents itself as a bunch of concentric 2D surfaces in 3 space. Now, we're not going to show in this class what you can do and how you would study these guys, but you should be aware of their existence, what they would kind of look like visually. And it just comes back to last class when we were sketching a bunch of stuff. Anyway, we are going to stop there. So today we spoke about multivariable functions, very basic stuff, what the concept of what it means to plug something in, what it means to have several independent variables, what the domain would look like, what a range would look like, what the graphs of surfaces would look like, and level curves, what level curves would look like. Level curves are important, not so much in 3D, although they can be in 3D because like topographical map is an application of the level curves right there, but they're even more useful in higher dimensions. Now, it's worth mentioning that a 5th dimensional figure would have level curves in 4 dimensions, so we can't even imagine what the shadow of something in 5 dimensions would look like. It's already too big for our human brains, which is why mathematics is important. Because the moment you start looking at a 5-dimensional object, that's just something with 4 input variables. Life is more complicated than something with 4 input variables. Are you kidding me? So we already get to a place where we can't visualize something that needs 4 inputs. And yeah, that's a problem. This is why we need mathematics. This is why we need things like vectors and so on and so forth, because graphing is lost to us. The world of graphing is lost to us once we go higher than, once we're at 3 variables or higher. All right, and we're kind of going to stop there. So the last half of today's lecture was more things that you had to know conceptually, but of course you should know how to plug in and sketch graphs of 2 variable functions. We're going to wrap up there. I thought we would start limits, but I guess the quiz took up too much time. We'll do limits tomorrow, and it'll be fine. We will.
I was planning to talk to you after class during office.
Yes,
I'm planning to talk to
I
you
remember you sent me a message. So I'll see you. Everyone else, have a good night. Stay safe. That's all I have for you guys today. Tomorrow, we are going to do limits and continuity in higher dimensions. Maybe we might get to partial derivatives, but if not, we'll do that on Wednesday. And I will see you guys in the
We
next
do it
one.
on Wednesday, like, you know, what are we doing on Thursday, actually?
Come again?
So, based on what I want to know, if we do partial derivatives on Wednesday, what are we going to be doing on Thursday?
Oh, something like a review, I guess.
Review?
Yeah, because our test is on Saturday. So we can either review for the second test, or we can start talking about the final. One or the other. I'll figure something out. That's for me to worry about, not you. Okay, all right. Finally, I
Bye.
will send you a link,
I'll see you
Jason, for office
after
hours.
during
For the rest of you, stay
class.
safe, and I will see you in the next one. Ciao.